So our next speaker is Sarah Kingsley from Georgia Tech, and she's a graduate student, PhD student there in the chemistry and biochemistry department. And the topic is real-time chemically specific monitoring and predictive analytics for onboard combustion events. And again, I'll give you a 1-minute warning.
Okay, great. Thank you. So good afternoon or good morning, everyone. My name is Sarah Kingsley, and I'll be presenting on our project. This has been a collaborative effort with myself, Dr. Thomas Orlando, and Dr. Brant Jones developing the instrumentation detection side of this, and Dr. Joseph Saley and Zhaoyu Xu developing the real-time data analysis side. So next slide, please. So the goal of this project is to develop a method for early detection of fires or near-fire events in space habitats using ambient mass spectrometry. And through our collaboration with Dr. Saley and Zhaoyu Xu, we're working to implement machine learning in the mass spectrometry data processing to allow for the autonomous identification of heat-related contaminants. So we've been studying the thermal degradation processes that common space habitat materials undergo. And what we found is that for many of these materials, before combustion or ignition occurs, a specific set of volatiles is released. And this volatile set can serve as an early warning sign of a fire or near fire event. So the workflow that we're trying to achieve is to detect these volatiles using ambient mass spectrometry, autonomously process the data, and alert inhabitants of the hazard. Next slide, please. So to develop proof of concept, we've selected 2 example materials that are commonly used on ISS. Teflon is found in wire insulations, spacesuits, cargo liners, and PET is the main chemical component of the Dacron and Mylar sheets that make up the insulation on ISS. Next slide, please. So for both these materials, we've studied the thermal degradation processes that they undergo and broke down these processes into a set of parts related to volatile emission. So both Teflon and PET undergo the same general pattern here. When they're heated to an extent, they'll release a certain set of volatiles. And if you continue heating the system, those volatiles will combust. So we're focusing mainly on our part 1 volatile production because this is what will serve as our early warning sign. And so by identifying, can you go back? Thank you. So by identifying the volatiles produced here, we can create a chemical signature for the thermal degradation of Teflon or PET. Okay, next slide. So once we've identified these volatiles, we want to study their production under different conditions. And to do this, we build a simulation that predicts what the mass spec data of these volatiles would look like under different temperature profiles using different sample masses. So here in these surf plots, we have the development of the chemical signatures over time as they would appear in the mass spec data. So we have Teflon on the left and PET on the right. I'm focusing just on the Teflon. Can you click, please? Thanks. Each one of these rainbow-colored peaks represents a Teflon-related component that has been detected in the mass spec. So we've isolated just the Teflon. And so on our x-axis, we have the masses of these components. And our z-axis shows the relative abundance. Our y-axis is showing time. So because we're detecting and analyzing this data in real time, we're able to see changes in peak abundance and composition as they occur. Now our YZ plane here is showing change in temperature over time. So what we can see is that during these processes, we produce more and more volatiles as you increase in temperature, but at some extent, we start to run out of our Teflon sample and the peaks begin to decay. Next click, please. And so in comparing the 2 plots, you can see that there is a difference in composition in the volatiles released by these 2 materials. And this is crucial because it's what allows us to identify the source material from the volatiles. All right, next, please. So I'm just going to briefly go over the machine learning classification that Xiaoyi Xu and Dr. Saley have developed and how they've been able to implement this in our project. So once we've studied the chemical signatures under different conditions, I usually send the data to Xiaoyi, who performs a classification using a machine learning model. Can you click, please? Thanks. So the first thing Xiaoyi will do is train the model. And to do this, he'll look at clean data, so just mass spectra of normal atmospheric gases. And then he'll create mixtures of the PET and Teflon data. And this gives us 6 classes to be recognized by the model. So looking at our contour plot here, can you click, please? Thanks. So from 0 to 200, we have clean data. And next click, please. From 201 to 1200, we have Teflon PET mixtures. And so you can see that the clean data looks pretty different, and you can tell what it is, but the mixtures here get pretty complicated. So next click. So to distinguish between these classes, Xiaoyi develops a 4 hidden layer deep neural network classifier. And so to operate this, you would input one mass spectrum, and the output is the classification of that mass spectrum. So is it clean, Teflon, PET, or a mixture? Next click, please. And so they've actually examined this model under cross-validation under different fold numbers. So how much of the simulated data is used to test versus how much is used to train. And they found that by using 90% of the data to train the model, they're able to classify the clean, Teflon, and PET data with 100% accuracy. So this is a pretty incredible tool that they've developed that allows us to both capture and accurately analyze this data in real time. Next slide, please. So right now, we're working on validating the simulation by collecting experimental data. So here in the image on the left, we have our mass spectrometer. And on the right, we have our sample heater and pulse valve. And so this system allows us to heat a sample and then send in pulses of air and volatiles emitted to the mass spectrometer for analysis. Next slide, please. So moving forward with this project, we're working to expand our library of materials using simulated and experimental data and publish our initial findings. In the long term, we'd like to be able to further analyze this data to extract more information about the fire or near fire event, like location, temperature, or rate of growth. We're also hoping to expand this technique to detect volatiles produced from other sources, such as equipment off-gassing or leaks or from mold and spores. Next slide, please. So I'd like to take a minute to thank the research team. Xiaoyi Xu and Dr. Saley have done a really incredible job developing this machine learning model and adapting it to process our data. And Dr. Tom Orlando and Dr. Brant Jones have also done some really amazing work developing the instrumentation for this project. I'd also like to say that this project is a part of NASA's HOME program, and so we really appreciate their support and their funding. Next slide. So thank you so much for your attention, and if there are any questions, I can answer those at this time.
Okay, great, thank you. So while Gary gets the next one up, we'll see. Any questions? I don't see any in the chat. So, well, how long do, so someone suggested it's, which other methods could be, a lot of, oops, got a lot of questions popped in. All right, so which other methods could be used to classify the measurements and why is machine learning needed? And the other person suggested it's overtrained.
I'm sorry, I think you.
So what other methods could be used to classify the measurements, and why do you need machine learning? I guess is a question that's.
Oh yeah, so that's a great question. So we are looking to do this, really quickly. And so when you get kind of a complicated set of mass spec data, the machine learning model is able to kind of identify the components or chemical signatures in that data in a matter of seconds. And so that really cuts down on kind of data analysis processing time, and it also automates the system. So it's, you don't need someone sitting there watching your mass spectrometer all day. So it is both for speed and for autonomy.
Okay, great. Well, we need. Thank you very much.